So welcome to this lesson about how to discretize a signal in the time axis. So how to convert a signal which is continuous in a sequence of numbers and how to come back to the continuous signal. So a continuous signal is like the one represented here. And if you want to convert this signal in a sequence of numbers, you have to take samples of this signal, usually at a time interval which is constant. It can be named capital T. And so you have, instead of a continuous line, you have a sequence of numbers that you can put also in a table. So n is the index of the sample and xn is the value of the sample. How can we mathematically express this operation? So suppose you take a signal which is a series of impulses. So the function g of t is made of many impulses. Each one of them has a distance with the neighbors of capital T. All of them are of area 1. And you do the multiplication of this series of impulses by the continuous signal x of t. So due to the properties of the impulse, what you get is again a series of impulses, but now the area of each one of these impulses is equal to the value of the signal in the position of the impulse. So you have the information of the value of the samples written in the area of the impulses. So you can take out this information and you get a sequence. So the multiplication of a signal by a series of impulses equidistant is able to obtain a sequence of numbers which is the digital version of the continuous signal x of t. Other very simple mathematics to be used to understand what is happening. So the first one is not so simple in the sense that the demonstration, you find it in the books and in many places, so I didn't report the demonstration in these slides. But property says that Fourier transform of a series of impulses is still a series of impulses. If the time interval between the impulses is capital T, the frequency interval between the impulses is 1 over capital T, which is the sampling frequency, so how many samples you have in 1 second. So this is one property that we will use. The second property that we are using is that when you do the multiplication of x of t, continuous signal, with a series of impulses g of t, you get at the end a series of impulses where the area of each impulse is the value of the signal at the position of the impulse. And finally, we are using also the other property which says that the product in the time domain is equal to the convolution in the frequency domain. So let's put together these three conditions in the sampling problem and try to obtain the Fourier transform of the sampled version of the continuous signal. So this xs at the beginning says this is the Fourier transform of the sampled version of the signal, which is obtained by doing the product of x of t by g of t, which is in the frequency domain the convolution. You have x on x of f is the Fourier transform of the original signal. That could be like this one in the blue, the Fourier transform of the continuous. And then you have the convolution with a series of impulses with the distance fs. And so this means that when you do the convolution, you are obtaining a lot of replicas of the original spectrum positioned at integer numbers of the sampling frequency. So instead of having just one blue line, you have many blue lines periodically repeating at the position fs, 2 times fs, minus 2 times fs. So you can see here which could be the problem. So there is a region where these replicas can overlap, or maybe they cannot overlap. So let's see this with an example. Suppose you have a signal, the Fourier transform of this signal is x of f, which is here, and you do the sampling of this signal with some sampling frequencies f of s. If the sampling frequency is less than 2 times the maximum frequency of the signal, you have overlapping of adjacent spectra. So the spectra of the sampled signal, the red line, is overlapping in some regions so that you don't have anymore the possibility to obtain the Fourier spectrum of the original signal. So this is a condition where you are losing information, you are not able to recover the original signal. Suppose that the sampling frequency is higher than 2 times the maximum frequency of the signal, so the replicas, they are well separated, and so you can obtain the original signal by some filtering of the central replica of the sampled signal. So having the samples, you can obtain the continuous signal without any error. So the condition is that the sampling frequency has to be greater than 2 times the maximum frequency of the continuous signal. How can you go back? How can you obtain the continuous signal from the discrete one? It's very simple, so you have to filter the sampled signal, and the filter is represented here by this green line. So you have to keep one copy of the Fourier transform, which is equivalent to the Fourier transform of the continuous signal. And depending on the transition zone, so depending on how big is Fs with respect to times Fmax, you can apply different kind of filters. I have some examples here. So one kind of filter could be the sample and hold. So you keep the sample for the whole period between two samples. You can do a triangular interpolation, which is the linear interpolation. You can do a cubic interpolation, a spline interpolation, and interpolation with a cardinal sinus, which is the ideal case. So depending on which one of these interpolators you are using, you have the equivalent transfer function, which is plotted here. So you see the transfer function of the ideal one, the last one, is this black line. And in this black line, you are very easily dividing the adjacent spectra. All the other filters have some leakage of adjacent spectra, and so the reconstruction will be not perfect. I am showing this sample. So suppose the original signal is a sinusoid, the blue line you see here. And suppose you want to sample this blue line becomes the samples you see here. And then you do the reconstruction with the holder, and the reconstruction with the holder is this stepwise line. So instead of the sinus, you get stepwise reconstruction. So it's wrong, because you are putting in the filter some adjacent spectra. If you do the linear interpolation, it's still something better than the holder, but still wrong. If you do the cubic, you are going closer to a better reconstruction. If you do the spline, still better. And if you do the ideal, you get completely the original sinus. So there is the possibility to go from the discrete time to the continuous time if you do the sampling with 2 times the maximum frequency of the original signal. And if the original signal has no maximum frequency, you have to filter before sampling, so that you are sure that you obtain at least the filtered version of the original signal. Let's go to the last slide. I want to show here that you can do the whole derivation of the signal theory on the digital signal domain. Digital signal domain means that you are converting the signals from the continuous time to the discrete time. So you have sequences. You speak about digital impulse response of digital systems. You speak about convolution sum. You speak about the discrete Fourier transform. But this is another course which is not held here. It's probably a totally new course and different from this one. Please remember that you can do everything in the sequence domain and then come back to the continuous domain by using the interpolators we have seen here. And this ends the lesson.